Okay, well, we're going to go ahead and start on what I usually refer to as the limit definition of a derivative. It's 2.7 in your book, and if your teacher is to be believed on the schedule, the section is entitled in the Stewart book, Derivatives and Rates of Change. Okay, but the basic focus in that section is limit definition of a derivative. And what we're going to do in this, the first video in this section, is I think it's important that we talk about sort of the conceptual backdrop of exactly what you're doing when you take the limit definition of a derivative and why. Okay? Now, remember that in times past, the only functions that we actually talked about slope for were linear functions. The only time when I told you find the slope was when we dealt with linear functions. And that's because linear functions have a slope that doesn't change. That's why they're lines, right? The only thing that you could tell when you got to curves, let's say we have this curve right here, something that looks kind of like a cubic, okay? The only thing that you could really surmise from this is sort of the general intervals on which the function is either increasing, meaning a positive slope, or decreasing, meaning a negative slope, right? But if I asked you, what is the slope of this function, you would have been like, yeah, you're crazy, man. The slope is all over the place. I mean, it's positive here, but they're different here. It's steeper here than it is here. So obviously this is going to be slope somewhere around, I don't know, 4 or 5, maybe 6 or 7. Right here the slope is going to be closer to, 1/2. What do you mean, what's the slope? You got to specify where, and then you got to tell me how to find it. Well, this is how we find it, okay? But before we start talking about the slope at a particular point, let's talk about the concept of average slope over a particular interval, okay? So if I want the average slope over the interval a to b, okay, what we do, and you may remember this from last year, what we do is we draw what's called the secant line, okay? The secant line that goes through a, f of a, and b, f of b, winds up being the average slope on the interval. And of course you know how to do this. It's just f of b minus f of a over b minus a. It's our old friend, the slope formula, right? So what we need from here, okay, so that should make sense to us. So if I go ahead and calculate the slope of that line, and you can sort of see it, and it sort of intuitively makes sense that the slope of that line is the average slope of that curve, right, on the interval. Now the conceptual leap is that we need to go from average slope and realize that average slope, if we're defining average slope on a small enough interval, okay, average slope winds up being the same thing as approximate slope, okay? Because as long as a to b is appropriately small, meaning it's small enough, if it's small enough, then this line right here approximates the slope of the curve for all of the points on that interval, including the endpoints, right? So if I gave you, and I said do not use any calculus, but give me the average slope at the point a, f of a, you would pick a point b, f of b, sufficiently close, and then calculate the average slope using the slope formula, and then just tell me on a small enough interval the average slope is approximate slope, okay? Now, if I can go to a small enough interval in order to get the approximate slope, and I know how to find that very, very easily, as long as I'm given the function in an analytic form, meaning I'm actually given the function in terms of its, variable configuration, I can go ahead and calculate that, right? But let's talk about average or approximate slope sort of in the abstract, right? not for any particular function, but just for any function in general. So if I want to talk about average slope or approximate slope in general, let's go ahead and let's sort of get the same sort of thing here. And I'll say, well, I want to find the slope at a f of a, okay? Well, if I'm looking for the slope at a f of a, okay, let's actually not call it a f of a. Let's just go ahead and call it x, and we'll call this f of x, okay? And instead of calling the next one b, we're going to go ahead and call that x plus h, so long as we're defining h as that distance right there, okay? So if I have x and f of x, and this winds up being f of x plus h, I now have an ordered pair, and since I've changed it from a and b to x and x plus h, I need to go ahead and rewrite the slope formula for that average rate of change. And of course, in the denominator, we're going to get x plus h minus x, which simplifies to just h. So this winds up being the approximate slope here. Okay? Well, we don't, in the end, want an average or approximate slope. We want the actual slope right here. Okay? So how do we get that? Well, the first step is to think about, well, I have an approximate slope. How do I get a better approximation? Well, if I want a better approximation, I have to redefine h as a smaller interval, right? And we'll cross those out, and this will be my new x plus h. And this right here will be my new f of x plus h. And of course, that new secant line winds up being a better approximation. Okay, well, can we continue this process? Can we continue to shrink h down in order to get a better and better and better and better and better approximation? And the answer is yes, okay? Now, hopefully all of you know where this is going, okay? First of all, because I'm sort of leading you there by the hand, and second of all, because you've seen it before. If we want to go from an approximate slope, okay, which is f of x plus h minus f of x, all of that over h, and we want to go to a accurate, okay, or an exact, accurate or exact slope, all we have to do is take the limit as that interval, the distance called h that we defined as the interval between those respective inputs. We basically need to drive that towards 0. And when we do that, we take it from the slope of the secant line to the slope of the tangent line. And in doing so, we wind up getting the instantaneous slope, the instantaneous rate of change at that particular point. Because the tangent line to a curve has the same slope as the curve at the point of tangency. I'm going to say that again. The tangent line has the same slope as the curve at the point of tangency, okay? And I've shown you this demonstration on Wolfram before, but I'm going to go ahead and show it to you again, because in light of our discussion that we've just had, I think it'll be a little bit more meaningful. Let's go ahead and show this. Now, you see the fact that this is a different function. It actually is analytically defined as y is equal to the square root of x, okay? And they, the mythic they, are asking for the actual slope, meaning the slope of that red line right there, because that red line is the tangent line at Q. And notice that the slope of the tangent line is the same as the slope of the curve at the point of tangency, which in this particular demonstration they call Q. And what we're going to do is we're going to just shrink it down, right? So if the p-value, your second value, is way over here, you see the fact that h is large, and you don't really have a very good approximate slope. But the more h shrinks, and the closer p gets to q, the closer that, I don't know, mustard-colored line, for lack of a, I don't know, is it mustard color? It's kind of brownish yellow. Whatever. That mustard color line gets closer and closer and closer and closer and closer and closer and closer, and the moment, boom, that h goes to 0, you wind up basically getting a secant line which has transformed itself into a tangent line, and therefore gives you the slope at that particular point. Now, how do we do that in the abstract? Well, we'll go ahead and do the example that's in that demonstration, root x, here in just a minute. But let's do one that's actually relatively simple. Let's do it for x squared, okay? Now, I know that in order to fit it into the formula, I'm going to need f of x plus h. Well, that isn't really all that difficult. You should have facility with function notation. I don't care what you plug in there. Whatever you plug in there goes in place of x, right? It could be f of puppy dog, and f of puppy dog equals puppy dog squared. It really doesn't matter, right? But I know that the derivative of f, which is, we usually use f prime, is equal to the limit as h goes to 0 of x plus h squared minus x squared over h. Now, this is going to make a whole lot of sense out of why we spent a bit of time dealing with limits and changing their form when we are given an indeterminate form. Because, go ahead and try to evaluate this limit. You're going to get x squared minus x squared over 0. 0 over 0. This is indeterminate in form. But if we go ahead and actually multiply that binomial squared out, we get that. Well, that winds up being rather helpful because this x squared and this negative x squared wind up canceling each other out. And then I have a common factor in that numerator once those x squared terms get canceled. I have 2x plus h times the common factor h. So I've sort of undistributed or factored out the greatest common factor h. And of course, this winds up canceling those h's. And now that I've changed the form, I can very easily evaluate this limit. Okay? When I plug in 0 for h, this is 2x. So the slope of x squared is 2x. And it makes sense that the derivative, which describes the slope or the rate of change of the original function, should be a function itself. Because the rate of change of x squared is not constant. The slope of x squared is not constant. The slope is variable. The slope changes. So what you've done here is you've taken f of x and you've run it through this limit definition such that it arrives at a variable expression, which of course expresses the slope of this particular function at any point. Meaning that if you were asked what the slope of f of x is equal to x squared is at 3, you would just plug 3 into the derivative function, and you would say, oh my gosh, the slope of that parabola at x is equal to 3 is 6. Okay? That's basically what's going on. That's the conceptual backdrop, and of course that's one example on how we actually walk through and sort of evaluate and sort of accomplish arriving at a derivative by limit definition. Now that is as far as we're going to go in terms of the sort of the conceptual backdrop, and that is of course just by way of reminder. Much of this stuff we went over last year, maybe not verbatim, but basically the general gist you should have captured last year, and this should be just by way of reminder. In the following video or videos, depending on how quickly I can execute them, the problems, not the videos. We're going to go ahead and go through as many problems as I think we need to of different varieties in order for you to have facility. Now remember, when you're working through these videos, the great thing about the fact that you're getting me on YouTube instead of in the classroom is the fact that you can pause me on YouTube. So if you want to do practice, go ahead and after I've laid out the problem, pause the video, try to work it out, and then let me work it out in the video and see if you've actually arrived at the correct answer. And that might be a good way to get a little bit of practice in. Alright guys, look for a couple more videos on this, and then we'll move on to section 2.8, and that'll round out your chapter 2 stuff for your upcoming test. Bye.